first thing we're going to do is introduce the basic workflow. So this is the Rhino Grasshopper combo. So here you have the Rhino viewport and the Grasshopper interface on the left here. So the workflow is modular. So we have 3 modules. The first one is going to be to generate the unit cell topology. This is just an example, so we'll get into the components available for each of these modules in a bit. So first of all, you generate the cell, or define a cell, and then you move on to the framing module, which will basically convert the cell, the list of lines here, into a format that it can use to populate a design space. So here the example is just a box, and you can play around with different parameters. We'll get into that later. And then finally we go to the meshing module, which will turn the wireframe into a valid mesh, so that can be printed. So just to show you guys. And so here you have like a pretty clean mesh. And then finally we have the report, which will tell us the validity of the mesh. So is it printable? So next we're going to break down each of these modules in order. So the next thing we'll talk about is the cell module. So the first option is just a built-in library. So we have a selection of unit cells. So we're planning on growing the size of this library to just about 20 topologies in the next few weeks. So pretty straightforward. The second option is to actually let the user define his own unit cell in any CAD software. So suppose I designed a unit cell and I import it. So I have this unit cell. Basically I'll just select all the lines, and then set them here. And then just to show you that so indeed we extracted the topology, and it can be used. Another thing to mention is that this component will actually return an error if the unit cell is not valid. So what is a valid unit cell? Right now we have one requirement. So there's 2 requirements, but one of the requirements will actually be fixed by our algorithm. So the first requirement would be that all the nodes have to be defined, and this. So for example, if we have an intersection, our algorithm will break down that intersection and split the lines and then create the node. But the other requirement that cannot be fixed is that each unit cell, so the opposing faces of a unit cell have to be identical. So for continuity, so imagine you're sticking this unit cell next to it. This side here, this face, has to be identical to this side, and the same thing for all three pairs of opposing faces. So if this is not the case, this component will return an error and not let you use the topology. The third option is again to give the user the freedom to design his own unit cells. So essentially it's just a Python script. So the user can define the nodes and then define the lines, so the relationships between the nodes. So for a simple example here, this is the popular octahedral topology. So in this case there is no error checking, so we assume the user knows what he's doing. So that's it. Those are the 3 options currently. So the next thing we'll do is look at the different framing components. So the first component is a conformed box, which is just a simple tessellation in the 3 Cartesian coordinates. Obviously you can use different topologies and play with the cell size and the number of cells in each direction. The next predefined design space is the cylinder, and we'll actually use cylindrical grid to populate the space. And you'll notice that when I use a small number of iterations in the tangential direction, I won't get the actual shape that I'm looking for. So the solution to that is to use our morphing parameter, which will actually morph the linear struts to the design space, in this case a cylinder. So again, you can play with the size of the design space and the number of iterations. And again, you'll notice that if I use many iterations in the tangential direction, I probably won't need to morph, because the difference will be almost negligible. But for very low number of iterations, I probably will need it. You see, so. All right. So the next three components we're going to look at are all for user-defined design spaces. So to start off, the surface-to-surface conformal component will take in two surfaces. So the space between these surfaces will be populated. So just to show you a simple example, so these design spaces were prepared in Grasshopper. So if we wanted to populate the space between these two cylindrical surfaces, the result would look something like this. And again, you can use the morphing parameter to morph to the design space. Obviously, we want the user to be able to import design spaces from any CAD software, and so that is actually possible. So I'll just disconnect these and load in a new design space. So here we have two sinusoidal surfaces, NURB surfaces, and so I'll just select these. And so here you see that we're conforming very nicely to the surfaces. Again, if I set morph to true, or false, sorry, so it was true, you'll see we're morphing more closely. Again, I can play with the number of iterations in each direction, and I'm gonna hide these surfaces just to make it clear. And so you see that we're conforming very nicely. So another parameter here is the flip UV. So sometimes the surfaces won't be aligned, so their UV maps will be about like 90 degrees off, so we might need that parameter in some cases. And again, different topologies. So the next user-defined design space would be the surface to axis. So here in this case we would be looking at a surface and an axis. So here you see that our axis is here and the surface. The result of that would look something like this. And again, the morphing parameter. And so all the same parameters as before. So the number of iterations in each of the UVW directions. For a second example, we could take this. This is just to show you that the axis doesn't need to be a straight line. It can be a closed curve or an open curve. finally, we have the conformal surface to point. So just to show you the design space here, so we have a sphere and a point, and the point doesn't necessarily need to be in the center. So here, this is what that looks like. So you see that the point is not in the center currently. So we'll just set morph to true, and then we can move the point around. I'll just show you the behavior. Finally, the last option we currently have is for closed design spaces, so reps or meshes. So in this case, we'll actually just generate a uniform mesh within it. A uniform lattice within it. So what that means, so take this design space, for example. We'll just generate a box in the bounding, a uniform lattice within the bounding box, and then we'll actually just trim it to the size we want. Another point here is that we have a plane parameter, so if you want a certain orientation of your lattice with respect to the design space, you can just input a plane here. The last thing we'll talk about is the meshing module, which basically takes the lattice wireframe and converts it to a solid mesh. So we can also play with the node size, so thicker nodes, and strut radius. So this is the homogeneous component. So basically the strut radius throughout the structure is the same. Again, we have the report here. So 0 naked edges and 0 non-manifold edges. What that means is that the mesh is watertight, so theoretically it can be printed. Obviously there's various constraints that come with the specific printing technology you're using. So we're open to having extra fields here. So for the minimum strut thickness, minimum pore size, for example. Also, I should mention that our components are based on Exoskeleton by David Stasiuk, and were adapted for our specific data structure. So the other option is the heterogeneous meshing component, which will basically have varying strut radius or density gradients. So here we have a cylindrical lattice, and we're going to generate a cylindrical gradient. So we want minimum strut thickness at the center and increasing as we go towards the outside. So here we set the axis of the cylindrical gradient to the z-axis, since our cylinder is aligned with the z-axis. And so what that looks like is something like this. So we'll see that the mesh is valid. We have no naked edges, no non-manifold edges, and we can also play with the maximum radius. And so now it's very obvious that there's a gradient. So we also have other types of gradients. I won't go into that. We're going to try and keep this short. Another point is that the FEA optimization comes in at the frame level. So let's say we have this frame here. We'll actually output a beam element model of this frame to the to an FEA software. So we have interfaces for Nastran and HyperWorks, and then based on the feedback we get from the FEA software, we'll adjust the radius of the struts at specific locations. So that's it. I think I've covered most. So thanks for listening.